Hello and welcome to this series of lectures. My name is Shirish Shevde. I am associated with the Computer Science and Automation Department at Indian Institute of Science, and I will give a course on numerical optimization. So, this course is about studying optimization algorithms and their applications in different fields. The field of optimization is very important and it has applications in lots of disciplines. See, in our day to day life we optimize things. For example, if you want to move from one point to another, we find out the path which is shortest, or suppose if you want to invest money, we find out those instruments where the risk is minimum and the gains are high. So, the process of optimization can be thought of as making best use of resources under given constraints. So, one definition of optimization is the procedure or procedures used to make a system or design as effective or as functional as possible. Not only human beings, even the nature has also a way of optimizing things. For example, the light rays follow certain path so as to reduce the travel time, right. So, why should one optimize different tasks, right. So, the optimization helps us to improve the quality of decision making. So, use of optimization tools help the policy maker to make better decisions, and the decision maker gains by doing so. As I said earlier, that it has applications in engineering, business, science, economics, military planning, etc. So, optimization is a very important field, and it won't be an exaggeration if I say that in everything that we do, we try to optimize. Okay. So, in this today's lecture, what I will do is I will introduce you to some of the preliminary ideas that we want to study in this course. So, I have tried to avoid the mathematical details as much as possible and tried to make it a very introductory lecture, but the details will follow in the later course. A mathematical program is basically a mathematical formulation of an optimization problem. So, a typical mathematical program would look like this: minimize f of x subject to x belongs to S, where x is a set of optimization variables, or they are also called optimization parameters. These are typically unknown. The f is a objective function which we want to minimize, and S is called a feasible region, it is also called a constraint set. So, we want to choose x within this set S such that some objective is minimized. Now, what is the solution of a mathematical program? Okay. So, we are looking for some x star which belongs to the set S such that the value of the function at x star is less than or equal to the value of the function at any other point in the set S. Okay. So, such a x star is called a solution of this problem, and f of x star is called optimal objective function value. Now, remember that x star may not be unique. For example, there could be some problems where you will have multiple solutions, and there could be some problems where the solution even may not exist. Okay. So, it is very important to check the existence of an optimization solution, optimization problem solution when we solve a optimization problem. So, in this course we will be working with a problem of this type. Now, in many situations you may have to maximize an objective function. For example, as I mentioned that when we want to invest money, we want to maximize the returns, right. But the maximization problem can also be equivalently written as minimization of minus f of x, and once we solve that problem, you change the sign of the objective function and you will get the solution of this problem. So, many times in this course we will restrict ourselves to minimization of a objective function, but truly it is not a limitation, because any maximization problem can be written as a minimization of a modified objective function. Now, this the optimization problem, the minimize f of x subject to x belongs to S, it can be compactly written in this form. So, this is the objective function, this is the x written below the minimization symbol is the optimization variable, and this is the constraint set. So, hereafter I will write the optimization problem as minimize f of x subject to x belongs to x in this form. Mathematical optimization, or it is also known as mathematical programming, it is basically a study of this problem formulations of this type. It is also a study of existence of a solution, and then use of algorithms to seek one such solution, and then the analysis of such solutions. So, this is called mathematical optimization or mathematical programming. Now, let us look at some interesting optimization problems that we come across in our day to day life. For example, if you are given 2 points A and B, and our aim is to find the shortest path between the 2 points A and B in a horizontal plane. Now, you will see that there exists plenty of or infinitely many curves which can connect point A to point B, right. So, this is the problem where we have to search over the infinite dimensional space to look for a solution of this problem, where we want to find out the shortest path between A and B. But suppose if we restrict ourselves to the Euclidean distance, then we know that the straight line path joining A and B will be the shortest path. So, a lot depends on the kind of distance measure that we want to use. Now, let us vary this problem a little bit. Let us assume that A and B are two cities, and they are connected by a set of roads. So, as you think of a situation where we have a network of cities, different cities, and A and B are two of those cities, right, and the cities are connected by a road, then the problem becomes little difficult. We have to look for the shortest path, because we want to travel on the road rather than finding out the straight line distance between the 2 points. Okay. Now, let us consider another problem. This problem also is called bus terminus location problem. Assume that PQ is a segment, rectilinear segment of a highway, and A and B are two cities which are on one side of this highway, and the problem is to construct a bus terminus on this section of highway, say bus terminus T, which is conveniently located to the residents of these two cities. So, which means that their travel time to the bus terminus should be as small as possible. Now, suppose if we decide to use Euclidean distance, then one has to look out for this path length, and then there are again infinitely many possibilities for the bus terminus T. So, one such possibility is shown here. So, the path length here is B to T dash and T dash to A. So, the problem is to find out the best position of the bus terminus, so that it is convenient to the residents of this cities A and B. Now, you might have seen a similar problem in geometry earlier, and also would have solved it using some geometry ideas, but then this problem also can be posed as an optimization problem. Now, the problem also can be extended to say 3 cities or 4 cities. Now, here is another problem. The points A and B are on a vertical plane, and there is a small ball which we want to roll from point A to point B, okay. And the aim is to find a path or to find a curve such that if the ball follows that path A, P, B, it will reach B in shortest time under its own gravity. So, there is no other force acting on this ball, and we are interested in finding out the curve which the ball should trace so as to reach B in the shortest possible time. There is another important problem in optimization, which is called the facility location problem. Suppose that A, B, C and D are 4 population centers in a city, and it has been decided to construct a facility which is located at some point convenient to all the population centers. For example, we want to construct a convenience store at certain place such that all the residents of these population centers can make best use of that thing. Now, suppose again we want to use the Euclidean distance. So, we basically want to minimize this the path length AP plus PB plus PC plus PD. The problem becomes more interesting when suppose there are sets of roads on which the traffic is allowed. So, that puts some constraints on this optimization problem. So, one has to find a proper location so that the road distance traveled by each of by residents from each of these population centers is minimized. Now, the similar ideas also can be extended to a different kind of problem. Suppose we want to have a garbage dump area for these population centers, and that should be as far away as possible from these population centers, but within the particular limits of that township, right. So, we want to maximize the distance of that garbage dump area from each of these population centers. So, so this problem again can be posed as an optimization problem. So, there is another interesting problem which typically is reported in the optimization literature, and that is called the transportation problem. So, here is a case of a company which is dealing with say agricultural related products. So, suppose the company has 2 plants, fertilizer plants which are called F1 and F2, and the company also has retail outlets. So, let us call them as R1, R2, R3. Now, each of these plants has some weekly capacity of producing a particular fertilizer, and each of the retail outlets has a weekly demand of the fertilizer that it should get from these plants. Okay. So, the transportation problem is to find out the best way to satisfy the requirement of the demand points using the capacities of supply points. So, these are the supply points and these are the demand points, and what is the best way to satisfy the requirements of these demand points using the capacities of these supply points. The problem becomes again more interesting if suppose let us call F1 as a fertilizer plant and F2 as a plant which packages seeds, and these seeds need to be supplied to these outlets instead of the fertilizer. Now, the fertilizer produced can be any real number, while the number of packets produced is an integer variable. So, the problem becomes a bit difficult because on one hand we have the real variables, and on one hand on the other hand we have the integer variables. Okay, so these fall under the category of mixed integer programming. We will see later more about this in the later part of this lecture. There is another interesting problem which is typically addressed by statisticians, and that is called the data fitting problem. So, from an experiment, a data set is generated which relates the dependent variable and the independent variable. So, suppose we plot the independent variable on the x axis, on the horizontal axis, and the dependent variable on the vertical axis. So, these are the data points which are obtained from some experiment. Now, they are assumed to have come from a particular function, and the idea is that from a family of all potential function models, find that function which best fits the observed data. So, this problem is very popular in statistics, also called the regression problem. So, you might have noticed that optimization problems are applied in a variety of domains, right from engineering to science to economics, statistics and business. So, some examples of these optimization problems are given here. So, one of the important problems is a scheduling problem. For example, airline companies would like to schedule their crews and the aircraft to minimize the cost. Diet problem is one of the oldest problems in this literature. So, every day we consume some food items and they have some nutritional contents in it. So, what is the optimal quantity of those food items that we should consume to satisfy the daily nutritional requirements and also minimize the cost. So, this is a well known diet problem in optimization literature. Then there is also a portfolio allocation problem, where the idea is to invest the capital dynamically in the portfolio of instruments, so as to have maximum returns. Another important application of optimization problems is engineering design. For example, optimization problems can also be used to design aircrafts, design aircraft engines, design VLSI chip designs, VLSI chips and so on. Optimization also has applications in manufacturing and robot path planning, and there are many more applications. So, you will see that optimization problems are useful in a variety of domains, and they are useful for the practitioner as well as a theoretician, and it is important to make use of some of the optimization ideas to take quality decisions and for the benefit of the business or whatever. Interestingly, optimization problems have applications in geometry, algebra and many other fields. So, this was the problem posed by Euclid in 4th century BC. So, in a given triangle ABC, inscribe a parallelogram ADEF such that the side EF is parallel to AB and side D is parallel to AC, and the area of this parallelogram is maximum. Now, you might have solved this problem using geometry ideas, but this problem can be posed as an optimization problem, and where we are looking for inscribing a parallelogram which has a maximum area. You also might have seen the arithmetic and geometric mean inequality. As you know that for any two non-negative numbers a and b, square root of ab is less than or equal to a plus b by 2. Now, this problem can be posed as an optimization problem. So, from this inequality you will see that the geometric inequality does not exceed the geometric mean does not exceed the arithmetic mean. So, the problem can be posed as find the maximum of the product of two non-negative numbers whose sum is constant. There is another interesting application in geometry where optimization problems can be used, is that suppose there is a company which manufactures the boxes for packaging, and the box is of rectangular size and it has a capacity of V units. So, the idea is to find the dimensions of such a box which has a capacity of V units, such that the surface area of that box is least. Okay, so, you might have seen that optimization is very useful. You might have solved these problems using different ideas, but they can also be solved by posing them as a optimization problem. Now, typical steps involved in solving a mathematical optimization problem are: the first step is the problem formulation, then to check whether the solution exists to such a problem or not, then solving the optimization problem using some algorithm if a solution exists, then analysis of solution, analysis of algorithm, and then one may have to go back to the problem formulation if there is a need, okay, or one may have to go to solve the problem using different algorithm if the algorithm that we have previously considered is too complex for the problem. Okay, so, this is the iterative process till we find out a reasonable solution, and such solutions will help the decision maker for his own benefit. Now, so the first and important step of any optimization problem is to minimize the objective function subject to certain constraints. Now, we will look at some of the problem formulations now. So, let us look at the bus terminus location problem, where the idea was to find the bus terminus on the segment PQ such that the lengths of the paths from lengths of the roads going from A and B to T are as minimum as possible. So, let us take it as a two-dimensional problem, and let xa1 and xa2 denote the coordinate of xa, and similarly for xb. And then this being a straight line, let us assume that its equation is ax1 plus bx2 plus c equal to 0, and we assume that we use Euclidean distance. Now, our aim is to find the location of the bus terminus. So, it will have two coordinates xt1 and xt2, these are called the variables. The objective is to minimize the distance from A to T plus distance from B to T. So, xa and xt are the coordinates of the points A and T respectively. So, distance between xa and xt plus distance between xt and xb. So, this is going to be our objective to minimize this quantity, and the constraint is that our bus terminus should lie on the line segment PQ. So, this is going to be our constraint, T lies on PQ. So, we can write this as minimize the sum of the distances subject to the constraint that the point T lies on the segment PQ. So, the coordinates of this point should satisfy the equation axt1 plus bxt2 plus c equal to 0, and xt1 and xt2 are the optimization variables here, which are determined by the optimal value of them. These are determined by solving this problem, and this will give us the exact location of the bus terminus which is convenient to the residents of the two cities A and B. Now, the problem can be varied a little bit. Suppose that instead of a straight line segment, the bus terminus should lie, the segment PQ is a curvilinear segment, and the bus terminus should lie on the that curvilinear segment PQ. So, if we know the equation of that curvilinear segment PQ, then we can use that equation instead of this equation, and reformulate the optimization problem. So, if you look at the facility location problem, right. So, if we say that xa, xb, xc and xd are the points belonging to the boundaries, Remember that I am looking at the boundaries of these population centers, and again we want to use Euclidean distance. So, the problem is to find out the best location of P, so that this location is convenient to the residents of these population centers. So, the objective is to minimize the distance between xa xp plus xb xp plus xe xp and xd xp. But what are the constraints? The constraints are that the points xa, xb, xc and xd should lie on the boundaries of the respective population centers. So, the problem can be written in this form. So, you will see that this is the objective that we want to minimize. These are the constraints that the points should belong to their boundaries, the respective boundaries, and the optimization variable is xp1 and xp2. Now, when it comes to the other problem of finding out the location for garbage dump area, we may have to change this maximization problem, a minimization problem to a maximization problem. The transportation problem also can be easily formulated. So, suppose let us first consider the case of two fertilizer plants F1 and F2 having capacity A1 and weekly capacity of producing A1 and A2 units of the fertilizer, and the retail outlets R1 to R3 they have a weekly demand of B1, B2 and B3 units respectively, right. And then to ship the fertilizer from the plant to the outlet, there is a cost involved, and let Cij denote the cost of shipping 1 unit of the fertilizer from the factory Fi to the outlet Rj. And then Xij, let Xij denote the number of units of product that needs to be shipped from the factory Fi to the retail outlet Rj. So, the Xij's are our variables, and the objective is to minimize the cost. So, if Xij is the unit and Cij is the cost of shipping 1 unit, so the cost of shipping the Xij units from factory I to retail outlet J is Cij Xij, and then we have to sum it over all possible combinations of factories and retail outlets. Now, what are the constraints? That every fertilizer plant cannot supply anything which is greater than its capacity. So, this constraint is shown here, and what is the retail, what is the constraint on the retail outlets? That they should at least get their weekly demand every time. Okay. So, their weekly demand for the jth outlet is Bj. So, they should get at least that much quantity of that much units of fertilizers, and also we need to ensure that all the quantities involved are, all the units produced, all the quantities shipped are non-negative. Okay. So, the optimization problem can be written as minimize the cost subject to the capacity of the capacity constraint for the ith factory or ith plant, the demand constraint for each of the outlets, and then the non-negativity constraints. Now, as I said earlier that if we change this problem a little bit, that the company also wants to sell the packaged seeds, and those packages are integers. So, this constraint has to be modified a little bit for this particular plant. We have to ensure that for this particular plant, the variables related to this plant are integers, and they are non-negative integers. So, that modification has to be made in this problem formulation. Now, when we look at the data fitting problem, so we are given the xi and yi, I going from 1 to n data points which are shown here, and it is also given to us that the most probable model is of the quadratic type, which takes the form ax square plus bx plus c. So, the idea is to fit a quadratic model given this data. So, a, b C are unknown parameters. So, they are also called variables, and the measure of misfit is the distance between the difference between the y and f of x. So, we want to fit a quadratic quadratic function to this data such that this objective is the misfit for every point is minimized. So, remember that there are no constraints given to us. So, there could have been some constraints on A, B and C, but nothing is given to us. So, we can write the optimization problem as minimize the misfit for every point, and minimization is done over A, B and C. So, these are our optimization variables. So, these are some ways of formulating the optimization problems. Formulating any optimization problem is an art, and care should be taken to formulate the problem properly, so that a lot of time is saved. So, the next step in the optimization process is checking the existence of a solution, but we will study this step later in this course. So, in today's lecture I will not talk about this. So, in today's lecture I will mainly concentrate on some of the preliminary ideas for solving a optimization problem if a solution exists. Okay. So, one of the simplest method to solve an optimization problem in one variable or two variables is a graphical method. So, we are now going to see this graphical method. Now, let us consider a function in one variable which is of this form: f of x is x minus 2 square plus 3, and the plot of the function is given here, and you will see that the minimum value of this function is somewhere here, and the corresponding value of x is 2. So, the minimum of this function occurs at 2, and the minimum function value or the optimum function value is 3. Let us look at another function. F of x is minus x square, which is plotted here. So, you will see that the function goes to minus infinity when x goes to plus infinity or x goes to minus infinity. So, the function does not have a minimum, but this function has a maximum, and the maximum function value is attained here, and the corresponding value of x is 0. So, you can see that the corresponding value of x is 0, and the optimal function value, the maximum function value is 0. Let us look at another example. F of x is x cube. So, you will see that this function when x goes to infinity, the function goes to plus infinity, and when x goes to minus infinity, the function goes to minus infinity. So, this function does not have a minimum or a maximum, because the function just goes to plus infinity or minus infinity in either direction. But at this point, so if you see that if you move in this direction on the right side, the function value increases, and if you move in the opposite direction or the other direction, the function value decreases. So, such points are called saddle points, and for solving any optimization problem, it is very important to locate such points. Now, a typical nonlinear function would have a graph of this form, okay. And if we are looking for the minimum of this function, let us assume that the function goes to infinity in both the directions. So, the minimum value of the function occurs here, but in many optimization problems, it is very difficult to locate such minimum points. Instead, if you look at these points, you will see that in the vicinity of these points, the function value is increasing, right. So, many optimization algorithms that we are going to study will try to find such minimum points. So, these are also called local minima, and we will formally define them later in this course, and such a point where the function value is the least, it is called a global minimum, and such minima are it is difficult to characterize such minima and also verify such minima. So, in this course we will mainly study about the solutions which are typically local minima. Now, when it comes to two-dimensional space, two-dimensional functions, so one function is given here. So, it is a function of two variables x1 and x2, and the function is f of x1 x2 is x1 square plus x2 square. So, the surface plot of the function is given here. So, now if we cut this function the surface plot horizontally, what we will get is a circle, and those circles are plotted beneath this surface. So, this is the x1 coordinate, x2 coordinate, and on the vertical axis is the function value, right. So, if we cut the surface horizontally, that means that we are fixing a particular function value, and that would result in what is called a contour plot. So, contour plot for the two-dimensional function is basically a set of point where the function value is constant. Now, if you cut this surface at different horizontal levels, you will get different contour plots, and some of them are plotted beneath this surface. Now, you will see that the function has a minimum somewhere here, which is a origin, and the function value is also 0. Now, let us just look at the contour plots and how do they look like. So, the contour plots for the previous function are given here. So, remember that this is a quadratic function. So, the outer plot which is given here, the function value is 8, and then inside the function value is 6, and then so on, and the minimum of the function occurs here, which is the origin. So, you will see that the function value in this case has been decreasing. Now, there is another function which is not a quadratic. You will see that this function has a peak and a valley, alright. So, so this valley will give you the minimum of this function, and this peak will give you the maximum of this function. So, the maximum occurs at 1 by root 2 0, and the minimum occurs at minus 1 by root 2 0. So, the same function's contour plots are given here. So, you will see that if you look towards the minimum, towards the left part of the curve, the function value keeps decreasing, and then the minimum is achieved here. The right part of the curve, the function value keeps increasing as we go in the interior, and the maximum occurs here. Here is another quadratic function. So, notice that unlike the previous quadratic function f of x1 x2 equal to x1 square plus x2 square, here the contour plots are elliptical in nature. So, again on this plot, the function value is constant, which is 8, and then as we go inside, the function value has been decreasing, and the minimum occurs somewhere here where the function value is 0. There is a commonly used test function in optimization literature, which is called Rosenbrock function, and then the contour plots of this function are given here. So, here the function value is this is the contour plot for function value 16, and then as we move in the interior, it goes down, and finally, the minimum is at 1 1, where the function value is 0. This is again a surface plot of some function. Now, you will see that it has multiple peaks and multiple valleys. So, optimization problem, it can be thought of rolling a marble along this surface, and then it will go to a point where the nearest minimum lies. So, if you roll it from this place, it will go and settle down at this place, or if you roll it from this place, it will go down and settle at this place. So, the initial point is very important in solving such problems. Now, beyond 2 dimensions, it is very difficult to use graphical methods to solve a problem. So, one has to resort to analytical methods or numerical methods. Analytical methods typically give you a solution in one go, while numerical methods will use some algorithm which are iterative in nature, and they will reach the solution over a period of time. So, we will look at some of the numerical methods, I mean the solutions given by the numerical methods. So, again we take a function which is quadratic, the contours are circular in nature, and suppose we start from this point, we some optimization algorithms can give you the solution in one go. So, if you start from this point, in the next steps the optimization algorithm will give you the solution which is 0.7 and 2. Now, if you take the some other quadratic function whose contour plots are elliptical, some optimization problems might give you a solution in certain number of steps. For example, if you start here, the algorithm might go to this place and then will go to this point and then so on, and then it will follow this zigzag path before reaching a solution. On the other hand, some algorithms might give you a solution in one step. So, a lot depends on the kind of algorithm that you want to use for a given function. Now, if you look at Rosenbrock function, so these are the contours of the Rosenbrock function. Now, suppose the initial point is say 0.6, 0.6. Then a typical optimization algorithm will follow this path, and then you will see the number of iterations required to reach the solution. Okay. So, it takes lot of small steps to go towards the solution which is 1, 1. On the other hand, if you again consider the same Rosenbrock function, but start from a point which is minus 2 and 1, right. Then see the path which is followed by the same optimization algorithm which was used previously. So, it starts from here, take a step to this point, and then takes lots of steps, and finally, it comes to this point, then goes to this point, again takes lots of steps to reach the solution. So, you will see that a lot depends on the initial point of the initial point that you choose for solving an optimization problem using numerical methods. As I have shown here that this algorithm would require the application of algorithm on this function would require less time if we start from here. On the other hand, if we start from here, it has to take many more iterations. So, depending upon the function, one needs to decide which algorithm to use. There are no generic algorithms to solve optimization problems. It all depends on how robust the algorithm is for a particular problem, and what is the computational complexity of the algorithm, and what is the information that the algorithm requires to solve a given problem. So, one has to make a careful decision about selection of an optimization algorithm to solve a given problem, and sometimes some algorithms may not even converge to optimal solution. Now, this was an unconstrained problem, and one solution to this unconstrained data fitting problem is shown here. So, you will see that we get a quadratic function by determining the optimal A, B and C, the parameters involved in the quadratic function. Now, there are different kinds of optimization problems. So, there are many more types, but I have listed the only few types here, because we will be concentrating only on a subset of these types. So, one type is called a constraint problem and the other one is called unconstrained problem. So, as I mentioned earlier that this is S is a constraint set, and we are trying to minimize the objective function subject to the constraint that x belongs to the constraint set. So, this is a constraint optimization problem. Now, if there are no constraints on x, then it becomes an unconstrained optimization problem. So, you will see that there is no S, the feasible region or the constraint set involved here. Many times these constraint optimization problems are solved by making use of the unconstrained optimization problems. So, it is important to study the unconstrained optimization problems first before going to the constraint optimization problems. Then the other types of optimization problems are continuous optimization problems and discrete optimization problems. So, in continuous optimization problem, the variables are typically real valued, while in discrete optimization problem, they are not real valued, but they typically can be integer values, or they even can take value from the binary number set, that is they can either be 0 or 1. Now, if we look at the fertilizer factories problem, so if both the factories are producing fertilizers, then you can call it a continuous optimization problem. On the other hand, if one factory is producing fertilizers and the other factory is packaging seeds of a particular plant, then it becomes a mixed problem, where one set of variables is continuous and other set of variables is discrete. There are other types of problems also. So, one of the problems is called stochastic optimization problem, where some or all of the problem data are random. So, in some cases the constraints also have they hold with some probabilities, and in such cases there is a need to define feasibility and optimality appropriately. So, for example, if you take this problem, so the data given to us, the weekly demands, the weekly capacities of the plants and the weekly demands, those may not be fixed, those could be random variables. Even the constraints also might hold with some probabilities. So, such problems are called the stochastic optimization problems. And then when there is no randomness in problem data and constraints, those problems are called deterministic optimization problems. So, in this course we will concentrate on constrained and unconstrained optimization problems, and in particular the continuous and deterministic optimization problems. So, the variables that we will be dealing with will be continuous, and the problems are deterministic. There is no randomness in the data, problem data as well as the constraint. There exist some kinds of optimization algorithms which are called locally optimization algorithms and globally optimization algorithms. So, if we take a general nonlinear function, as I mentioned earlier, that these are the local minima, even this also can be a local minima. So, many algorithms try to find one such local minima. So, you can think of it as using a ball, and if you put a ball at this place, it will roll down to this point. On the other hand, if you put a ball here, it will roll down to this point, and if you put it here, it will roll down to this point. So, based on your starting point, the solution that you will get or the local minimum that you will get will be decided, because all these algorithms that we plan to study in this course typically try to go towards down the function towards the nearest possible minimum, and there is no mechanism for the algorithm to go up the curve. On the other hand, there are some optimization algorithms which are called global optimization algorithms. So, which will give you a global minimum with some probability. But in this course, our main focus will be on local optimization algorithms, where we start from any arbitrary point and go downhill and go towards the nearest possible local minimum. Remember that the local minimum and global minimum will be formally defined later in this course, but this is just to give you an idea about what we plan to study in this course. Now, here is the overview of the topics that we plan to cover in this course. So, the subject of optimization requires some mathematical background on differential calculus, linear algebra, and a bit of analysis. So, we will try to cover some of those topics in this mathematical background. Then we study the one dimensional unconstrained optimization problems, and then move on to multi-dimensional unconstrained optimization problems. This one dimensional unconstrained optimization problems are useful in solving this multi-dimensional problems. So, we will first study one dimensional and then go to problems for multi-dimensional. Then we move on to the multi-dimensional constraint optimization problems, and some of these problems can be solved using techniques of unconstrained optimization, and then we move on to active set methods and penalty and barrier function methods. Now, there are some good references in the optimization literature. So, books by Fletcher, Cambo, then Leuenberger are quite popular. The book by Nocedal and Wright also addresses this topic of numerical optimization. There is also a book by Suresh Chandra Jayadeva and Mehra. So, these are some of the reference texts that one can use for studying some topics in optimization. There are many more books, but because of the space limitation, I have not included them here. There is a interesting book written by Tikhomyrov, and the title of the book is Stories about Maxima and Minima. It was initially published by American Mathematical Society in 1990 and republished by Universities Press in 1998. So, this has some of the interesting problems related to optimization and belonging to different fields. So, one can also look at some of the problems in physics, geometry, algebra, analysis, where the mathematical optimization problems can be used. So, in the next part of the course, we will start with mathematical background. We will start with the vector spaces and a bit of linear algebra, and then move on to differential calculus, something about functions, and then the convergence of sequences and so on. And then we move on to the one dimensional unconstrained optimization problem. So, in this today's talk, I just wanted to give a brief introduction about what we plan to study in this course, and let us continue in the next class. Thank you.